Good morning, sir, and all my dear friends. My name is Aryan Mahakalkar from third year electrical department. Today, we are going to present the topic of single phase, semi, and full converter with R and RL load. There are seven members in our group: Aryan Mahakalkar, Shravan Andraskar, Harsh Jadhav, Kunal Ghodmare, Utkarsh Agarkar, Tanushri Langde, and Mohnish Thakre. Next slide. So these are the points we are going to cover in today's presentation. First of all, we are going to cover the introduction. Then we are going to cover history, power factor improvement technique, extension angle control, symmetrical angle control, pulse width modulation, sinusoidal pulse width modulation, single phase semi converter with R and RL load, single phase full converter with R and RL load, advantages and disadvantages, application. Then at last we are going to cover numerical. Next slide. So my name is Aryan Mahakalkar and I am going to cover today introduction and history. Next slide. A rectifier is an electrical device that converts alternating current AC, which periodically reverse direction, to direct current DC, which flows in only one direction. The reverse operation is performed by the inverter. The process is known as rectification. Since it is strengthened the direction of current physically, rectifier takes number of forms, including vacuum tube diodes, wet chemical cells, mercury arc walls, stacks of copper and selenium oxide plates, semiconductor diodes, silicon-controlled rectifier, and other silicon-based semiconductor switches. Historically, even synchronous electromechanical switches and motor generator sets have been used. Early radio receiver, called crystal radios, used cat's whisker of fine wire placing on a crystal of galena lead sulfide to serve as a point contact rectifier or crystal detector. Rectifier have many uses but are often found serving as component of DC power supplies and high voltage direct current. Power transmission system rectification may serve in role other than to generate direct current for use as a source of power. As noted, detectors of radio signals serve as rectifier. In gas heating system, flame rectification is used to detect presence of a flame. Depending on the types of alternating current supply and the arrangement of the rectifier circuit, the output voltage may require additional smoothing to produce a uniform steady voltage. Many applications of rectifier, such as power supplies for ratio, television, and computer equipments, requires a steady constant DC voltage, as would be produced by a battery. In this application, the output of the rectifier is smoothed by an electronic filter, which may be a capacitor, choke, or set of capacitor, choke and resistor, possibly followed by voltage and regulator to produce steady voltage. More complex circuitry that performs the opposite function, that is converting DC to AC, is called inverter. Next slide. Before the development of silicon semiconductor rectifier, vacuum tubes, harmonics diode, and copper oxides or selenium-based metal rectifier stacks were used. With the introduction of semiconductor electronics, vacuum tubes rectifier become obsolete except for some enthusiasts of vacuum tube audio equipments. For power rectification from very low to very high current, semiconductor diodes of various types, junction diode and Schottky diode, etc. are widely used. Other devices that have controlled electrodes as well as acting as unidirectional current fall are used where some more than simple rectification is required. For example, where variable output voltage is needed, high power rectifiers such as those used in high voltage direct current power transmission employ silicon semiconductor device of a various types. These are the thyristor or other controlled switching solids state switches which effectively function as diode to pass current in only one direction. Next slide. So now we are going to cover the history. Diodes were the first semiconductor electronic device. The discovery of crystal rectifying abilities was made by German physicist Ferdinand Bryan in 1874. The first semiconductor diodes, called Cat's whisker diode, were made of crystal of minerals such as galena. The silicon control rectifier, that is SCR or thyristor, proposed by William Shuxley in 1950. The mercury arc rectifier was invented by US electrical engineer Peter Cooper-Hewitt at the turns of 20th century. The diode bridge circuit was invented by Polish electrotechnician Karol Polak and patented in December 1895 in Great Britain and in January 1896 in Germany. Next slide. Remaining points will cover by Shravan Understood.
Hello, my name is Shravan Andraskar and I will going to cover the topic power factor improvement techniques. In this, I will cover extinction angle control technique and symmetrical angle control technique. First of all, we will see about power factor improvement techniques. So, what is power factor? So, it is the apparent power upon real power. So as we consider the control converter, the important part is ripple content, which depends on the firing angle, which is generally low, especially at low output voltage range. As the ripple factor increases, the power factor increases. So the power factor of phase control converter depends on delay angle, as I said. Second, these converters generally generate harmonics into the supply. Force commutation can improve the input power factor and reduce the harmonics level. This force commutation can be uh, can be generated by applying a freewheeling diode in a circuit. These force commutation techniques are becoming attractive to AC to DC conversion of voltage. The basic techniques for the power factor improvement based on force commutation are extinction angle control, symmetrical angle control, pulse width modulation, and sinusoidal pulse width modulation. Now we will see the extinction angle control. Uh, this technique can be used for single phase semi converter and full converter with the load R resistance and inductive load. So in this slide, this figure shows the single phase semi converter where thyristors T1 and T2 are replaced by the switches S1 and S2. The switching action of S1 and S2 switches are performed by the GTO, that is gate turn on thyristors. These thyristors is switched on by applying small positive gate pulse and can be turned off by applying small negative gate pulse. In this extinction angle control, the switch S1 is turned on at omega t is equal to 0 and is turned off by force commutation at omega t is equal to pi minus beta, where beta is an extinction angle Thus, for 0, thus for omega t greater than 0 and less than or equal to pi by beta, pi minus beta, the switch S1 and diode D2 conducts. If the load is sufficiently inductive, in if the load is sufficiently inductive to maintain constant ripple free load current, the load current is continued through freewheeling diode FD after omega t is equal to pi minus beta up to omega t is equal to alpha. In this slide, the waveforms, uh, the waveforms after the input voltage is given, it is shown. In this, the gate pulse is given at omega t is equal to 0 and is turned off at omega t is equal to pi minus beta, and then the thyristor T2 and the switch S2 and thyristor T1 are then turned on at omega t is equal to pi and is turned off at omega t is equal to 2 pi minus beta. Now we will see the symmetrical angle control technique. In this technique, the thyristor is allowed to conduct symmetrically in positive half cycle, that is, if it is fired at firing angle alpha, then by force commutation it is turned off at omega t is equal to pi minus alpha in the same positive half cycle. In this, there are in this switch S1 is turned on at omega t is equal to alpha and turned off at omega t is equal to pi minus alpha, and switch S1 is turned on at omega t is equal to pi plus alpha and turn off at omega t is equal to 2 pi minus alpha. For turning on and turning off of thyristors, that is GTO, the gate signals are generated by comparing half sine waves with a DC signal. By changing the magnitude of DC signal, the conduction angle beta can be changed. If beta is the conduction angle, then thyristor is turned on at omega t is equal to pi by 2 plus beta by 2 and turned off at 2 pi minus beta by 2. If the for ter, if the DC signal magnitude Vc is increased, beta is reduced and vice versa. From the waveform of the input current Is, it is seen that the fundamental component Is1 is in phase with input voltage and therefore displacement factor is unity. Therefore the power factor is improved. In these control techniques, the input voltage leads and the power factor is leading. In this slide, for symmetrical angle control, the graph is plotted for the respective circuit diagram. As I said that the gate pulse is given pi at pi minus beta and turn on at pi plus beta. So next, the other two techniques, that is pulse width modulation and sinusoidal pulse width modulation, this will explain by Kunal.
Hello, my name is Kunal Ghodmare, and I will cover the topic pulse width modulation and sinusoidal pulse width modulation. Next slide. Pulse width modulation. is a technique that generate variable bit pulse to represent the amplitude of an analog input signal. The output switching transistor is one or more of the time for a high amplitude signal and of more of the time for a low amplitude signal. In the converter, employing phase angle control, extinction angle control, or symmetrical angle control, there is only one pulse per half cycle in input current, and therefore the lower order harmonic is filtered. The lower order harmonic filter out, the lower order harmonic can be limited or reduced by varying pulses per half cycle. This is done using the pulse width modulation technique. Increasing the number of pulses result in increasing the magnitude of higher order harmonic, but this could be easily filtered out in pulse width modulation technique. Next slide. In this, the JITO are turn on and turn off several times during a half cycle, and the output voltage is controlled by changing the width of pulses. For turning on and off, the gate pulses are generated by comparing a triangular wave with a DC signal. First pulse start at alpha 1 and end at alpha 1 plus delta 1. Second start at alpha 2 and ends at alpha 2 plus delta 2. Next slide. In sinusoidal pulse width modulation is a technique of pulse width modulation used in inverter. An inverter generates an output of AC voltage from an input of DC with the help of switching circuit to reproduce a sine wave by generating one or more square pulses of voltage per cycle. In PWM control, the output voltage is controlled by varying the width of pulses. However, the width of all pulses is same. If there are p pulses per half cycle, the maximum pulse width is pi by delta. It is possible to choose the width of pulses in such a way that their certain harmonic could be eliminated. In sinusoidal pulse width modulation technique, the pulse widths are generated by comparing a triangular voltage, that is VR, or amplitude A, and frequency FR with a carrier half sinusoidal voltage Vc of variable amplitude AC and frequency twice of Fs. The sinusoidal voltage Vc is in phase with the input supply voltage Vs and has twice the supply frequency Fs. In this sinusoidal pulse width modulation technique, the power factor is improved because the displacement factor is in unity. For 4 pulses per half cycle, the lowest order harmonic is in fifth, and for a 6 pulse per half cycle, the lowest order harmonic is in seventh. Thus, the lower order harmonics are eliminated or reduced. Next slide. Uh, the width of pulses and hence output voltage are controlled by changing the amplitude. In this, we will use the modulation index varied from 0 to 1. Modulation index means the ratio of amplitude of carrier signal, which is AC, to amplitude of reference signal, which is AR. Next slide. Next slide will be explained by Harsh.
So, myself, Harsh Jadhav, and I am going to conduct the topic that is single phase semi-converter with R and RL load. Next slide. So, first of all, we will discuss about single phase semi-converter with R load. Following figure shows the circuit diagram of single phase semi-converter with R load. In this semi-converter, two SCRs and two diodes are connected in symmetrical configuration. For positive half cycle, the current flows from Vs to T1 to R to D1 to Vs, and for next negative half cycle, the current will flows from Vs to T2 to R to D2 to Vs. Next slide. So now we will discuss the operation. Uh, in operation, there are three modes. In mode 1, it conducts from alpha to pi. In mode 2, it conducts from pi to pi plus alpha. And in mode 3, it conducts from pi plus alpha to 2 pi. So let us discuss about mode 1, that is alpha to pi. In mode 1, during positive half cycle of AC input voltage, thyristor T1 and diode D1 conduct, and thyristor T1 is fired at omega t is equals to alpha. Therefore, the average output voltage is equal to the instantaneous supply voltage, and load current flows through T1 R D1 and back supply again. Now in mode 2, that is pi to pi plus alpha. In mode 2, at instant omega t is equals to pi, the supply goes through 0, and after pi, supply voltage reverts its polarity. Due to reverse supply across conducting devices T1 and D1, they turn off at omega t is equals to pi, and this type of turn off is called as natural or line commutation. Therefore, the average output voltage is 0, that is VO is equals to 0 volt, and load current is also 0. In mode 3, that is pi plus alpha to 2 pi. In mode 3, at instant omega t is equals to pi plus alpha, the supply voltage becomes completely negative. That is, during negative half cycle of AC input voltage, thyristor T2 and diode D2 are forward bias. Thyristor T2 is fired at omega t is equals to pi plus alpha. Thus, the average output is equal to instantaneous supply voltage, because due to conduction of T2 and D2, the load is directly connected to supply, that is VO is equals to Vs. The load current flows through T2R and D2. Thyristor T2 and diode D2 conduct up to 2 pi. At omega t is equals to 2 pi, commutation takes place due to natural zero appearance across supply. Next slide. So now we will discuss about the mathematical expression. First expression is average load voltage VDC. VDC is equals to Vm by pi in bracket 1 plus cos alpha. The next expression is for average load current, that is IDC. IDC is equals to Vm by pi r 1 plus cos alpha. Next expression is for RMS load voltage, that is VRMS. VRMS is equals to Vm by root 2 1 upon pi in bracket pi minus alpha plus sine 2 alpha upon pi 2. Next slide. Next slide. So the next topic is single phase semi converter with RL load. Following figure shows the circuit diagram of single phase semi converter with RL load. In order to get controllable DC output voltage from the rectified circuit, phase control rectifiers are used. The control rectifier are also known as AC to DC converters. They employ thyristor whose triggering angle is varied to get a controlled DC output voltage. In a semi or half controlled converter, one quadrant operation is obtained, that is, only positive voltage and current will be obtained at the output. For positive half cycle, the current flows from Vs to T1 to R to L to D1 to Vs, and for negative half cycle, the current will flows from Vs to T2 to R to L to D2 to Vs. Next slide. Uh, Now we will discuss the waveform and mode of the operation. During positive half cycle of AC input voltage, T1 is fired at omega T is equals to alpha. The current flows through load. The inductance L is assumed to be sufficiently large to produce continuous load current. Thyristor T1 and D1 conduct during this period. In this mode of operation, the load voltage and load currents are positive, so the inductive load will store energy. Now at omega t is equals to pi, the supply goes through zero, that is supply voltage reverses its polarity. Therefore, the conducting thyristor T1 try to turn off, but due to presence of inductance at load side, it will try to oppose any change in currents flowing through load. The self-inductance voltage will bring the same diode D2, which is connected in series with SCR T1. Now the D1 get turned off, and in this mode pi to pi plus alpha, the D1 and D2 conduct. Due to conduction of D1 D2, the load is short circuited and the load voltage becomes zero. This mode of operation is called freewheeling mode of operation. Now the during negative half cycle of AC input, D2 already conducting and thyristor T2 is fired at omega T is equals to pi plus alpha, and load directly to supply, that is load voltage is equal to supply voltage. Current flows through T2 through load T2. In this way the operation is repeated. Next slide. Now we will see the mathematical expression. In both the single-phase semi-converter circuits with and without freewheeling diode shown above, the source supplies the power to load from alpha to pi. From the above waveforms, upon neglecting the drops of diodes and thyristor, the average output voltage can be found from VDC. VDC is equals to Vm by pi in bracket 1 plus cos alpha, and the expression for Vrms is equals to Vm by root 2 in bracket 1 by pi in bracket pi minus alpha plus sine 2 alpha by 2. Next slide. Next slide. Now next slide will be explained by Sean. Utkarsh. Explained by Sean. Utkarsh.
Hello all, my name is Utkarsh Agarkar and I am going to brief the topic of single phase full converter with R and RL load. Next slide. Following figure shows the typical circuit diagram of single phase fully controlled bridge rectifier with R load. It consists of 4 SCRs T1 and T4 and they are connected in bridge type configuration driving the resistive load. The single phase fully controlled rectifier allows conversion of single phase AC into DC. It is used in various applications such as battery charging, speed control of DC motors, and front end of UPS, and as well as in SMPS. The current cycle of the circuit diagram will be starting from the source, and then then the current will flow through thyristor T1, and after thyristor T1 current will flow from resistor, and after that it will go to thyristor T2 and it will get back to the source. It is for positive half cycle, and for negative half cycle current flows from the path Vs, then it will go to thyristor T3 and then to resistor and then to thyristor T4 and it will get back to the source. Next slide. The operation of single phase fully controlled converter consists of three modes, that is mode 1, which is from alpha to pi, mode 2 which is from pi to pi plus alpha, and mode 3 which is from pi plus alpha to 2 pi. Now we will see about the mode 1 which is from alpha to pi at omega t is equals to 0 instant. The supply voltage goes through 0. After omega t is equals to 0, the supply goes towards positive, that is during positive half cycle of AC input voltage. Thyristors T1 and T2 are fired at omega t is equals to alpha. Thus the average output voltage is equals to supply voltage, that is that is V0 is equals to Vs. The current flows from point L through thyristor T1 through load resistance through T2 to point N. The load current is positive and has same shape of AC mains input voltage. The load voltage and load current are in phase at omega t is equals to pi instant. The supply voltage goes through 0. The conducting SCRs T1 and T2 are turned off due to natural commutation. At this instance, both the load voltage and load currents are 0. Now we will come to mode 2, which is from pi to pi plus alpha. At omega t is equals to pi, the supply becomes 0. After omega t is equals to pi, the supply voltage reverses its polarities. Therefore, in this mode of operation, no any SCRs conducts. Both load voltage and load currents are 0. For mode 3, which is from pi plus alpha to 2 pi, at instance omega t is equals to pi plus alpha, that is during negative half cycle of AC input voltage, the SCRs T2 and T4 are fired at omega t is equals to pi plus alpha. Therefore, the load is directly connected to supply voltage, and average output voltage is equals to instantaneous supply voltage, that is V0 is equals to Vs. The load voltage is positive and load current is continuous positive. The SCRs T2 and T4 continue to conduct up to 2 pi. At omega t is equals to 2 pi, the supply goes through 0. So conducting thyristors T2 and T4 will turn off at omega t is equals to 2 pi due to line natural commutation. Next slide. Now we will see the mathematical expressions for average output voltage, that is VDC. VDC is equals to Vm by pi 1 plus cos alpha. Expression for average output current IDC is equals to VDC upon R, that is equals to Vm by pi R 1 plus cos alpha. Expression for average RMS voltage VRMS, that is Vrms upon root 2 in bracket 1 upon pi in bracket of pi minus alpha plus sine 2 alpha upon 2 raised to the power half. Next slide. Expression for average RMS current, that is IRMS, is equals to Vm by root 2 into R in bracket of 1 upon pi in bracket pi minus alpha plus sine 2 alpha upon 2. Next slide. Now we will see the topic single phase full converter with RL load. Following figure shows the typical circuit diagram of single phase fully controlled bridge rectifier with RL load. It consists of 4 SCRs T1 to T4 and they are connected in bridge type configuration driving highly inductive load. Inductance L is used in a circuit to reduce the ripple. At firing angle alpha is equals to 60 degree, T1 and T2 thyristor T1 and T2 starts conducting. Current flows from Vs to T1, thyristor T1, and then to resistor, then inductor, and then thyristor T2, and it will get back to the source. At firing angle is equals to pi plus alpha. thyristor T3 and T4 will start getting conducted, and the current will start flowing from Vs to thyristor T3, then to resistor, then to inductor, and then to thyristor T4, and it will get back to the source. Next slide. In this slide, we will see about the input and output voltage and the current waveforms. The operation of single-phase fully controlled converter consists of four modes. Mode 1, which is from alpha to pi. Mode 2, which is from pi to pi plus alpha. Mode 3, which is from pi plus alpha to 2 pi. And mode 4, which is from 2 pi to 2 pi plus alpha. Now we will see about the mode 1, which is from alpha to pi. During positive half cycle of AC input voltage, leaf point L is positive with respect to cathode. Therefore, thyristor T1 and T2 are fired at omega T is equals to alpha. Thus, the average output voltage is equals to the instantaneous supply voltage. In this mode of operation, the shape of load voltage is identical to that of supply voltage. The load voltage is positive and constant. The load current is also positive as that of supply current IS. Both load voltage and load current are positive. The inductive load will store energy. Now for mode 2, which is from pi to pi plus alpha, in this step of operation at instant omega t is equals to pi, the supply goes through 0, and after pi radians, supply reverses its polarities and it will become negative. Therefore, the conducting thyristors T1 and T2 will try to turn off due to natural reversal of supply voltage. Through the natural commutation, due to this stored energy in inductive load, it will oppose any change in the current flow to the load. So thyristors T1 and T2 will continue to conduct in negative half for some period. In this mode of operation, the load voltage becomes negative and the load current is always positive, continuous and constant. Both load voltage and load current are opposite in polarities, so the stored energy in inductive load will return back to the supply again. Now for mode 3, which is from pi plus alpha to 2 pi, at instance omega t is equals to pi plus alpha, the conducting thyristors T1 and T2 are turned off due to natural commutation. At the same time, other pair of SCRs T3 and T4 are fired at omega t is equals to pi plus alpha. Therefore, the average output voltage is equals to instantaneous supply voltage. The load current is instantaneously transferred from one pair of SCRs T1 and T2 to other pair of SCRs T3 and T4. In this mode of operation, both load voltage and load currents are positive. The inductive load will again store the energy. Now for mode 4, which is from 2 pi to 2 pi plus alpha, at instance omega t is equals to 2 pi radians, the input voltage goes through 0. After 2 pi, it becomes positive. That is, during positive half cycle of AC input, the conducting thyristors T3 and T4 try to turn off. The inductive load will oppose any change in current through it. In order to maintain the load current constant and in same direction, a self-induced voltage appears across the load. This maintains conducting thyristor T3 and T4 forward bias. In spite of change in polarity of supply voltage, the load voltage becomes negative and equal to supply voltage, whereas the load current continues positive. Therefore, load acts as the source, and the stored energy in inductive load will return back to the supply again. Next slide. Now we will see about the mathematical expressions. First is the expression for average output voltage VDC. VDC is equals to 2 Vm upon pi into cos alpha. Expression is for average load current, that is IDC. Next slide. IDC is equals to 2 Vm by pi r into cos alpha. Next slide. Expression for the RMS load voltage, that is Vrms, is equals to Vm by root 2. Next slide.
Myself Tanushree Langde and I am going to cover advantages of improved power factor and disadvantages of low power factor. Next, next advantages of improved power factor. So let us first of all discuss the principle of improved power factor. The basic principle of improved power factor is connected a device which take leading current in a parallel with the inductive load to neutralize the effect of lagging current. In order of power factor improvement, the method was some taking a leading power should be connected in parallel with the load. Some such device or capacitor. The power factor improvement aim to optimize and utilization of electric power factor, reduction of a electricity bill, also power losses in the circuit. In the article, so first see the first improvement increases in the efficiency of system and device. In most industry processing facilities use may industry motor to drive their the pump and other machinery in the plant. The many electric utilize companies assess the power factor penalty for the lower power factor and some also inductive high power factor. By adding the power factor and corrective can eliminate the power factor and penalty from your bill. Next improvement is a low voltage drop. In this, with an improved power factor, the voltage drop in the conductor is reduced, improving the voltage of the equipment. Reduction in the size of conductor and cable which reduce the cost of copper. In financial return from the conductor losses reduction alone is insufficient to justify the installation of capacitor. It is sometimes the alternative additional benefit, especially the older plant. The article was organized and published 24 May 2017 and was review and update and 25 May 2022. Next one improvement is an increases is available power. Also line losses is reduced. Next is the appropriate size of electrical machine. For example, transformer and generator etc. Uh, and next improvement is eliminated the penalty of low power factor from the electric supply company. The reduction in current flow the resulting from improved power factor may allow the circuit of carrying new loads, saving the distribution of network when the extra capacity required the network when the extra for the additional machinery or equipment, saving your company and thousands of dollars in necessary but the cost. Uh, Next improvement is low of kilowatt. The many electric until company the charge of maximum demand based on either the highest registered demand kilowatt or percentage of highest registered demand in the kilowatt per ampere. The improving power factor thought power factor is correction will be lower the demand and charge, helping to reduce the your electricity bill, as well as saving the power bill. uh, also the better uses of power system lines and generator. In this case, a lower power factor causes the higher current flow for given load, as well as the line current is increases the voltage is drop. And last one improvement is the saving energy as well as rating of the cost the electric device and equipment is reduced. Next. So let us please see the disadvantages of low power factor. In this case, low power factor is mainly due to the induction load, and industrial mostly inductive load are used, likely induction motor, lamp and etc. For the various purpose in the inductive load take the lagging current, hence result is low power factor. The low power factor has mainly distributed therefore power factor improvement necessary to get the right problem and associated with the low, low power factor. So first disadvantages of line large line losses. We know that the line losses is directly proportional to the square of electric current. Next one is a large kilowatt rating and size of electric equipment. As we know that the almost all electric machinery like transformer, alternator, and switchgear etc. are rated in kilowatt ampere, but it is clear from the low power factor is inversely proportional to the kilowatt ampere. Third one is a greater conductor size and cost. In this case, the low power factor is currently is increases, thus so the transmit is high current and we get the large size of conductor. Also, the cost of a large size of conductor will be increases. Fourth is a power voltage regulation and uh, large voltage uh, large voltage drop, as well as the low efficiency. Uh, in this case, the low power factor, there will be the large voltage drop and large line losses, and this will be causes system or equipment efficiency too low. For instance scenarios, due to the low power factor, there will be large line losses. Therefore, the alternator needs the high extension, thus generator efficiency as well as transformer efficiency will be low. And last disadvantages of low power factor, the penalty form of electric power supply on low power factor. Electric power supply imposes a penalty of power factor below 0.95. Lagging electric power factor will be so must improve if above 0.95. Next, next slide explain by Mogesh.
So applications and numerical we will see in next slide. So next, applications of converter. All of you are know about um, most of the applications. Let's see first application, and the convert half wave and full wave converter using mobile phones, laptop and charger circuits. Then again it is using UPS to convert AC to DC. Our home inverters are also good example of this converter, means converter using that also to convert AC to DC. LCD, then LED TVs. Again in car alternators to charge the battery during the running of the car. and then it is used in a driver circuit also, soldering iron circuit, and firing circuits are based on the converters principles. And then uh, firing circuit, soldering iron circuit, okay. uh, Amplitude modulation radio circuit as a detector. Then it include paper mills, textile mills using DC motor drives, and DC motor control in steel mills. It is again used in automation industry. AC fed traction system using a DC traction motor, electrometallurgical and electrochemical process reactor controls. Next, let's see numerical based on single phase half wave rectifier. Uh, the single phase half wave rectifier has a purely resistive load of R, and delay angle alpha is equal to pi by 2. Then we have to find VDC, IDC, VRMS, and IRMS. VDC is nothing but Vm upon 2 pi 1 plus cos pi by 2 equal to 0.1592 Vm. We will get the value in terms of Vm cause the value of Vm is not given in the numerical. Then IDC equal to Vm upon 2 pi r 1 plus cos pi by 2. It will 0.1592 Vm upon r. Then Vrms equal to Vm by 2 under root of 1 upon pi minus pi by 2 plus sine 2 pi by 2 upon 2. It will 0.3536 Vm. So here you just need to put the value of alpha, and then you will get this value of Vrms. Then again value of RMS we will get from the formula Vm upon 2r under root of 1 upon pi minus pi by 2 plus sine 2 pi by 2 upon 2. It will be 0.3536 Vm by r. We can see Vm by r and Vm by r in IDC and IRMS are constants. So next, a numerical 2 half control rectifier. So where in this numerical the value of V is given to 30 volt, and operating frequency is 50 hertz. Firing angle, we'll see about firing angle, alpha equal to pi by 6, and purely resistive load of 20 ohm. And then we have to find the average output voltage, RMS value of output voltage, rectification efficiency, and average load current. So the value of Vm will under root of Vs equal to 3.26 volt. Next, average output voltage. Average output voltage VDC is given by formula Vm into 1 plus cos alpha by 2 pi. Here alpha is a firing angle. By definition, it is given as the angle in the AC cycle at which the thyristor start conducting at the application of the positive voltage to gate is called firing angle. It is denoted by alpha, and by putting the value of alpha pi by 6 and putting the value of Vm, we get 96.59 volt, which is equal to VDC. Then RMS value of output voltage, you need to just put the value of pi, and that is value of alpha, and that is pi by 6, and value of Vm in VRMS of formula, you will get 160.27 volt. RMS value of output voltage. Next, then the term is rectification efficiency. Generally, efficiency is a ratio of output to input. Rectification efficiency is given by ratio of output DC power to the input AC power. And for a half wave rectifier, rectification efficiency is 40.6%. If a value of PDC and PAC are equal, then it is considered as a no harmonics disturbance in the circuit, and it is considered as a 100% of rectification efficiency, which is an ideal condition, which is not um, seen in the practical or in general purpose. The efficiency is given by PDC upon PAC. The average output power PDC is given by VDC into IDC. VDC we already calculated, it is 96.59 volt. Next, then average load current IDC is given by VDC by R, will get 4.82 amperes. Then PDC 96.59 into 4.82, that is 96.59 into IDC, 466.48 watt. The output AC power is given as PAC equal to VRMS into IRMS. VRMS 160.27 volt and IRMS, as you can see, 8.013 ampere. Next. So previous slide we discussed about efficiency, n equal to 466.48 upon 1284.32, which is PAC, and PAC is calculated by 160.27 into 8.013. Then efficiency is found to be 0.3632. Percent efficiency is nothing but divide by 100, so it will be 36.32%. Next, this one numerical on full wave control bridge rectifier has input of 120 volt, RMS at 60 hertz, given frequency is 60 hertz, and 20 ohm of resistor. Delay angle is 40 degree. So we need to calculate here current in the load, power absorbed by load, and the source volt ampere. As in the earlier slide we have seen formula for VDC. You need to just place the value of alpha 40 degree and value of VM 120 into root 2, we will get 95.4 volt. IDC is equal to VDC by R, and it is found 477 by 477 ampere. IRMS equal to VM upon R, and by putting this value in the expression, as we seen as we have seen in previous slides, it is found 5.80 ampere. And then power absorbed by load, I square by R, 5.80 square into 20, 673 watt. Then RMS current in the source is also 5.80 ampere. Apparent power of the source is S equal to V RMS IRMS 120 into 5.80, it is 696 volt ampere. Then the value of P by S equal to 674 upon 696 pound to 0.967. Next, you can get more information from these websites. These are for your references and sources. Okay, next. Thank you very much.